Welcome back to the classroom. My name is Mr. Wong. In today's lesson, we are going to look at what is power, how do we define it in physics. I'm going to be focusing on this particular dot point here, conduct investigations of a range of mechanical processes to analyze qualitatively, so descriptive-wise, and quantitatively, calculation-wise, the concept of average power given by the following formula. Just to show you the dot point of reference here, this is the syllabus outcomes, and this was the dot point we're going to look into today. Our main focus is the scenario of uniform accelerated rectilinear motion, objects raised against the force of gravity, and work done against air resistance, rolling resistance, and friction. So let us begin.
Have a look at this situation here. We've talked about it before. What is work? Work is defined as the force that you apply to displace an object. Now, on this graph, you can see the object and the force is moving in the same direction. So they are parallel to each other. The force and the displacement are both parallel to each other. That's what we define as work being done. That's what the double line here means. We're looking at the parallel force to our displacement. If the object is originally stationary and now it's starting to move, that means not only are we causing work, we're causing a change in kinetic energy, because if we have a moving object, we have kinetic energy. That's how it's defined. Let's try and change the situation up here. You have the compare the pair, same mass of weights, same displacement of weights, same work is done, same change in kinetic energy. However, what you can see is the rate in which they are doing this work is different. So we know that the work done is the same on both sides. So the change in kinetic energy is the same on both sides. But what's not the same is the change in time to cause them to lift the dumbbells or the weights. And we define this rate of which energy is being used up to move something as power. So if you think of energy as the ability to do work, so energy is just the ability to do work, then power is the rate of energy that you use to do that work. So energy, ability to do work. Power is the rate of energy used. Okay. If we compare the pair again here, we have two horses. Doesn't really matter how heavy the horse is at the moment. That's besides the point of our situation. We have two weights, the exact same mass. They're going to be lifted and displaced by 1 meter each. However, the time taken is 1 second to pull this weight up. The time taken to pull this weight up is 2 seconds. So we can say that because this one takes, or the change in time is smaller compared to this side, the power is higher. Obviously, another thing you could see here is energy output in electrical appliances. Now, some of you might have paid attention when you go to the shopping center and buying new washing machine, dishwasher, and you'll see these little star efficiency ratings. Now, these ratings are done in terms of power. So next time you see one of these, and obviously the higher the stars or more stars you have, the better the rating, which means if you have higher rating, so if you have more stars, this power output and input should be lower than if you have a low efficiency, so a lot less stars in general. What that means is for every wash you do, or for every minute you have the washing machine on, you'll be using less power, so less energy is used if you're using less power per minute, or less energy per minute. And so that would save you quite a bit in terms of your electricity bill. Now, assuming that most of you still live with your parents and all that, I guess that's not something to consider. But if you do move out one day, this will be one of the things you look at in terms of buying the appropriate equipment to do your washing and washing your dishes and all that. So now we can confidently say that power is just a change of energy over time. Remember, delta means change. That's the same thing as saying the change or the work done. Work done is just the change in energy anyways. Power is measured in watts, named after the guy who looked into it, James Watts. Work done is still in joules, energy in joules, time in seconds. 1 watt, if you try to put it into an equation, work done is in joules, so J. Change in time is S, okay? So 1 watt is the same thing as saying 1 joule per second. So put this into idea, it's joules per second. If you ever come across questions where it says kilojoules per minute, then you'd have to convert it into joules per second to get the correct SI units. We're going to try and also derive a relationship between power and force. Can you show this formula? Can you show that power and force and velocity are related to each other? I'll give you some hints. You can use the following equations. Okay, let's try and derive it out ourselves. So power, we have it here, force is equal to, or work is equal to force times displacement. If I substitute W away with Fs, I get that power is equal to force over, or force displacement over time. If I do a little trick that we do in maths, is we remove this fraction away from each other, S over T. Displacement over time. What is that? Velocity equals to displacement over time, which means the power is the force times your velocity. And so you get that. So that's how we got to FV. Now, remember, we are still talking about the parallel force, so the direction in which the object is moving. If you have a look here, we also have is cos theta. Don't forget, we are looking at the component of where the force is moving. So we still keep on using the theta sign here as well, depending on the situation, of course, but we will get to some of those in a second. If you ever do a graph of energy versus time, if you have a look at this, so energy, time, change in energy over change in time. If you try and find the gradient, you'll find that it is the power. Okay? If you try to work out the area here, okay, that would be energy times time. That's not really a unit we have, so we don't worry about that. If you have a graph where it is power over time, power times, or power over time, if you calculate the area, that'll give you energy. Okay, so if I'm calculating power times the time, P times delta T, that equals to energy. So you could see by the way of how you graph or plot the diagram, one plot, energy times time, will give you power as the gradient. Okay. If you plot power over time, the area will give you energy. And so that's what we come to our conclusions with power. Power is just change in energy over time. It also equals to force times velocity. And that force is implied to be parallel to where the object is moving. So the velocity, say the velocity is moving in this particular direction, the force is also moving in this direction as well. And so if our force is moving in a particular direction, we also need to make sure we find the appropriate unit to match up with it. And so that's where the cos theta comes in. Okay? Power is given in watts, also joules per second. Work done in joules, energy in joules, time is seconds, velocity is meters per a second. Remember, this is the same thing as saying m-s. Okay, we come to our measurements of power. You might hear when people are driving, they say has blah blah blah. This car has so much amount of horsepower, 50 horsepower or whatever. Now horsepower is equal to 745.7 watts. What does that actually mean, a horsepower? It just means if a horse was to lift, it's an old empirical unit, if a horse was trying to lift an object 550 pounds up 1 foot in 1 second, that's technically what a horsepower is. In terms of how they measured it back in the day or how they define it, don't really remember, but you can always search that up. Objects raised against the force of gravity. So now we're going to look at some calculation questions. We're going to try and use this bulk of equations here to look at if we pick up an object and rise it up or pull it up against gravity, what will we get? So let's have a look at some of the questions here. Question 1, we're trying to find the power given the conditions. And then question 2, we want to look at the amount of work done and the power output provided as well. So let's go through those. Question 1, a box with a mass of 2 kilograms is carried up 5 meters. Make sure you are also underlining what the question has in terms of the values. We have it done in 20 seconds. Calculate the power required for this task. Assume G is 9.8. Okay, so the force, we know we need to firstly work out work done. So we're trying to work out work done to find power. Now work done is given by the parallel force displacement. Our box is being shifted up, so it's going up like so. Okay. And assuming we're not looking into angles, so the mass is 2, so m is 2. G is 9.8, so let's plug this through the calculations. We find that the weight force is 19.6 newtons. Okay. How far have we displaced? Well, the displacement is 5 meters. So the work done, if we plug that in now, in total is about 98 joules. Okay? So that's the amount of work that's been done to lift our object in 5 meters. The last thing we need to do is find the power. We already know what the work is. That's 98. 98 over our time, which is 20. So put that in as well. And so I've used 4.9 watts of power to do this. Okay, question 2. A student of mass 40 kilograms walks briskly up a flight. Alright, I'll try that again. A student of mass 40 kg walks briskly up a flight of stairs to climb 4 floors of a building, a vertical distance of 12, in a time interval of 40. What's the rate the student is doing the work against gravity. Okay, so we're trying to look at gravity again. We know that m in this case is 40, g is 9.8, and then the total displacement is 12 meters. Okay, substitute that into our formula. That's what we've done. It's asking you the rate at which work is being done, which means in this question we're trying to look for power. Power is work over the change in time. The work we've done is 4,704 joules. Okay, the time interval for us to do all that is 40 seconds. So substitute that in, and we get 117.6 watts. Question B, if the energy is transformed by the leg muscles and the student is exerting or outputting 30 kilojoules every minute, what is the student's power output? So we know that power is given in units of watts. Watt is given in units of joules per second. What we have is kilojoules per a minute. So we got to convert the kilojoules into minute. Remember, from joules to kilojoules times by 1,000, from seconds to a minute, that's a difference of 30 as well, or difference of 60. So, whoops. So from kilojoules to joules times by 1,000, from minutes to seconds times by 60. Okay? So here we have it. So it's going to be 30 kilojoules times 1,000, 1 minute times 60. And that's what we have with this working out here. And so the total power output from the legs is 50 or 500 watts. An interesting little topic in terms of power. In year 12, you talk about things like transmission lines and how power lost from generators all the way to transmission lines. We come up with a nice little formula here. P equals IV. So you'll come across this probably later on in year 11 anyways. But the power carried by electricity is dependent on the voltage and the current of the electricity. What we also know is during the course of electricity being transported in these wires, okay, there will be some kind of resistance in the wires. And due to this resistance, some power is going to be lost from the electricity, and so you won't get the complete 100% transformation of energy from the generator all the way to us. That will not happen because of some resistance in the wires. Now what we know is the factor that influences this is actually current. Why not resistance in this case? Because obviously the resistance is constant for the wires. But if we increase the resistance, so if we increase the current, of the wires, so if we're increasing the amount of electric charges flowing through, these charges will agitate the wires, so all the little atoms in the wires, and that's where the heat is generated. That's where we lose energy because of heat loss. So how do we combat this? Well, you can see that voltage is not part of the equation here. And we know that in this equation, if we increase voltage, okay, we can essentially decrease the amount of current available. So what actually happens in real life is you would increase the voltage from the generator all the way pretty close to us, and then they reduce that voltage and increase the current back again. So that's how they kind of do that, convert from high voltage to low voltage towards us. From the generators, it's high voltage equals to low current. Towards us, they reduce the voltage to increase the current again. Just a touch. Let's look at another question, and it is looking at power in uniform accelerated rectilinear motion, rectilinear, is objects moving in a straight line, so in a single line plane, like this little trolley car moving along the table, which is kind of a prac that we would do, but obviously we're not having a prac lesson here. All right, so we have a rocket-powered trolley, 500 kilograms, has a violent velocity of 150, initially at rest, so there you go already. We know there is some form of acceleration we can look into. And then in 3.2 seconds is the time taken for it to occur. Okay, let's have a look at the equation here. You can see that I've given you the equation for some assistance. Why is that the case? Why don't we have initial? Remember, change in kinetic energy is the final velocity minus the initial velocity. Now the initial is at rest. So if it's initial, u is 0, so this is 0, so this is 0. So all you're left with is the final velocity and the mass. Okay, so that's why we can do that. The mass in this case is 500. The final velocity is 150. So I substitute that in, and I get that it is this value here. So that's the amount of energy of this trolley as it goes from rest, from u equals to 0, 3.2 seconds, to 150 meters per second at the end here. So that's quite a lot of energy being used up there. B is asking you what's the power delivered by the rocket engine. So we already know that's the change in energy we have here. How long did it take? 3.2 seconds. So plug that in. That is how many watts of power we generated. Now you might see this as a really big number. You might want to reduce it a little bit more. Sometimes what they do try and rewrite is convert it into kilowatts. So if I try and convert it into kilowatts, it'd be 1,758 kilowatts, or you can do it in scientific notations, whichever suits you as well. Then question 4, we have a 160 kg sledge. So a little sledge like so. It is applied, a force is applied onto it, inclined at 35 degrees. So we have a force of 75 newtons at an angle of 35 degrees, like so. Find the work done by the force in moving the sledge for a distance of 120 meters. So the assumption would be the displacement we have here is 120. Find the work done by the force. Okay. All right. So we know that the force we're trying to look into is the parallel force. In this case, this particular direction is our parallel force. If we assume this to be a right angle triangle, you can see what I'm trying to do here. The relationship between F parallel and 75 is the cos sine function. So F parallel is equal to F vector, the vector that we're looking at, cos theta here. Okay? And that's how you go through that. Let's try and do this on the other slide. So redraw this again. This is what we're dealing with here. And our displacement is 120 meters. Okay, so I know what the force is. It's 75. Displacement is 120. And cos theta is 35 degrees. So if I substitute that in to my equation, that's what I have. And so the total joules I have, if I round it off to one decimal place, is 7,372.4 joules. Okay? So that's the total work done by the force moving my sledge across. All right, next question is, If this takes 2 minutes, find the average power delivered by the force. 2 minutes needs to be converted into seconds, so that would be 2 minutes times 60, so 120 seconds. Substitute your work done into here, and there you have it. And the power output, or the average power delivered, is 61.4 watts. And that's what you can do with questions of rectilinear motion. Last one we're going to look at in terms of scenarios is work done against air resistance, rolling resistance, friction. So we'll go through a couple of these examples. Rolling resistance is where a car, let's say, is rolling against the floor, or the car wheels rolling against the road. Air resistance obviously comes to particular importance when developing sports cars, racing cars, and stuff like that. So question 5, we have a car of mass 1,500 kilograms. It is traveling at a constant speed of 20 meters per second. The combination of the air resistance and the rolling resistance gives a retarding force of 500 newtons. Calculate the power required. Okay, so we need to work out firstly what's the net force being applied on our car, and that will help us work out the total power the car is exerting. Okay, so the idea is we are constant speed. So if it's a constant speed, it means the net force is equal to 0. All right, remember, according to Newton's law of motion, an object will stay in motion or constant speed unless you apply external force or external unbalanced net force. So our net force has to be 0 here, which means the applied force and the drag force we experience should add up to 0 overall. Okay, so we'll come over here. So if the drag force or the retarding force in total is 500 newtons, that's the friction or drag we're experiencing here. So if I move the drag over to this side, okay, the applied force is essentially my negative drag force. If I call my drag force instead of saying 500, I'd say that's the negative direction, so I'll say it's minus 500. Then the applied force is 500 newtons. Okay, I'll say that again. Our net force is constant, so our net force is 0 because we're traveling at a constant speed, which means the force applied and our retarding force, when added together, will equal to 0. Okay? Let's assume that the retarding force, so the force against motion, okay, force against motion is the negative direction, and that the applied force is the positive direction. And so that's why it's plus 500 newtons. All we do now is also put in force times velocity. So the force is 500, velocity is 20. And so I get 10,000 watts of energy being used for our car to maintain the speed. The last question looks like a long question, but it's broken into 2 parts. Okay, and let's try and work it out together like so. So in question 6, a lorry of mass 1,500 kilograms moves along a straight horizontal road. So we can have some object, a lorry moving along a road. It experiences a resistance of 750 newtons. So 750 newtons is going against it. It has a total power output of 3,000 or 36 kilowatts or 36,000 watts. Okay, find the acceleration of the lorry. Okay, if we also had a speed of 20 meters per second. So we know that the power is 36,000 watts. We know that the velocity is 20 at that particular point in time. We can then find what F is. So I can put that like that. Remember, just substitute your numbers in. There's no harm in substituting the numbers in and then rearranging the equation. The total force is 1,800 newtons from the lorry. But the lorry also experiences a friction force. Okay, so the lorry itself is producing a force of 1,800 to go forwards, but it has 750 newtons of friction going against it. So we need to subtract those together. And so the total net force is 1,050 newtons going forwards. Now that we know what the force is, we can use Newton's second law of motion to work out acceleration. And acceleration is just force over mass. So 1,050 over 1,500, that's the mass up here. And so the acceleration it experiences is 0.7 meters per second squared. If we move on to the next question, which is using the same properties as the last equation, it says find the rate at which the lorry's engine is moving now if it is going against a 6% incline horizontal hill or incline hill. Okay? So if I draw this out, our object, the little lorry, is going up here, 6% incline going that way. We need to know the parallel force. Okay? So the direction or the actual displacement, whatever, so it's going this way. Okay? So we need to know what this force going up in that particular direction is doing. Okay? In this particular section here. So we need to find the weight force. So mass, grams, mass and gravity is the weight force. Mass is going to be 1,500, that's from last question. And acceleration due to gravity is 9.8. And then we need to find sine 6. So the force of lifting our object up is 1,536 newtons, roughly around so, give or take with the decimals. Now we need to know, because the question is saying we need to find a constant speed at 20 meters per second. So if it's a constant speed, it means the net force is 0, okay? So what that implies is our object, not only does it have this amount of force pulling it up, but obviously there is some kind of frictional force at 750 pulling it back here. Okay, so if the forces aren't balanced, then obviously our object is not maintaining a constant speed of 20 meters per second. So what we need to do is we need to not only look at how the force we need to reach and go up the slope, we also need to consider the amount of force we also need to have to overcome this friction force going against us. Okay? So I need to add the force of going up the slope and the force going against friction, which is basically the opposite value of what friction is here. That will give me the force I need, the net force I need to go up this slope at a constant velocity and a net force of 0. And so this is what I get here. Okay? So the net force applied is the force going up plus 750, which is 2,286.6 newtons. Roll it over, we have a speed of 20, and so we have about 45.7 kilowatts of power if you want to write it in kilowatts, or this value if you want it in watts.
And that concludes our lesson for today. Just remember, today we talked about power is the rate of change in energy. It's the change in work done over time. And we also demonstrated the relationship between power and force and the motion of an object. So until next time, take care and see ya.